Hello, good morning everybody. Welcome to the seminar. Today I'd like to talk through some aspects of designing secure microcontroller systems. Over the last year or so, ARM has been rolling out their Mbed OS operating system, which is designed to be an operating system for the Internet of Things. This consists of a number of components, a remote server which has a device connector, and also an Mbed client which is designed to go into small embedded devices. Clearly, for such a system, we need this to have a very high level of security. So within the Mbed device client, there are a number of interesting features to implement security for small microcontrollers. The two major items in here are the Mbed TLS, or Transport Layer Security, which provides a set of cryptographic functions that provide a high level of security between the client endpoint and the server connector endpoint. And also within the device is a small microvisor which provides isolation for critical parts of the system. So the microvisor effectively provides a small container that provides an isolated region that defends secure data and secure functions against network-borne attacks. You may have joined one of our earlier seminars which discussed the Cortex Trust Zone, which will come in with ARM v8. So we will have a look at that at a later date, and this microvisor is likely to become a separate component in its own right. However, today we'll have a look at the Mbed TLS component, which is really a library of cryptographic functions. As I say, it provides support for secure sockets, transport layer security for TCP, and also UDP communication. But it's highly modular, so that we can use some of the algorithms that are inside of it for our own applications. And this is available as a free component, and it's published under the Apache 2 license. So we can use it on Cortex-M and also Cortex-A devices. So when we look at security within a small microcontroller, or any device really, there are a number of things that we need to bear in mind to protect our data. First of all, we need confidentiality, so that we want to make sure that that data is only accessed by authorized individuals. We also want to have means to check the integrity of that data as well, so that we know that the data we've received hasn't been interfered with or modified in any way. We want to make our data always available to authorized users. Again, in a system, there's nothing more frustrating than trying to access something that you're entitled to and being banned. And also, we want to provide non-repudiation as well, so that we can prove not only the integrity, but also the origin of that data as well. So we'll have a look at some of the algorithms that will help us achieve those ends. It's also worth noting, when we start to look at cryptographic systems, that there is a principle called Kerckhoff's principle that says that the security of a system must depend on the secrecy of the key and not the secrecy of the algorithm. So that any security algorithm that we're going to use, we should be able to publish it, people should be able to study it and find weaknesses in it. Whatever you do, don't try to invent your own encryption algorithm, or indeed use a proprietary secret encryption algorithm. That's generally a recipe for for a bit of disaster. So stick with well-known and well-trusted algorithms. So within the Mbed cryptographic security component. We have a number of algorithms, a number of symmetrical ciphers. Also, it supports public key cryptography, public key infrastructure with X509 certificates. We can also do hashing to provide data integrity, and an extension of hashing is message authentication codes so that we can prove the integrity and also the origin of data as well. Underpinning many of these algorithms are random numbers, so again there's a certified random number generator included as well, and also a number of useful support functions that we may be interested in using in our own applications. So in terms of encryption, decryption algorithms, there are two major types: symmetrical key algorithm, where the same key is shared at the origin and destination, so we need to have a secure channel to swap that key. Also asymmetrical key encryption, where we have one key to encrypt the data and a separate private key to decrypt it. So in theory this allows us to send the public key to an insecure channel, so the data can be encrypted and sent back to us. All of these encryption algorithms are what are called block encryption algorithms, in that they'll take a block of plain text data, encrypt that data, and then provide a block of encrypted data. So over a large amount of data we can encrypt it in successive blocks and send that to our remote destination, or we can protect data at rest in a similar fashion. So this simple mode, called electronic codebook mode, or ECB, as I say, uses the encryption algorithm. However, it's encrypting over blocks of data which can reveal patterns in our data, which are an aid to cryptanalysis for people trying to break our encryption algorithm. So there are a number of additional modes that these ciphers can work in. So typically we can use something like block chaining mode, where we encrypt a block of data, and that output block of data is then exclusive ORed with the next block of data before it's encrypted, and so forth. So we're masking patterns in our data by chaining all of these blocks together. And then we have an initialization vector, which is a block of data which is used to encrypt the first, which is sort of exclusive ORed with the first block of data to start the process. So in this system, the initialization vector can be public, and again it's only the key that needs to be kept secret. So the disadvantage of this system is that all of the blocks are dependent on one another, so any corruption in any block or loss of a block of data means that we lose the whole message. So again, it's a good way to make the encryption scheme stronger, but we have to guarantee that we receive everything and all of our data is correctly ordered. Within the advanced encryption standard, there is another method similar to the CBC mode, where we have a counter mode, where again, rather than using data from the previous block, we use a random value generated by a counter, which is exclusive ORed with all of our plain text data. The advantage of this mode is that we can parallelize this so that we can encrypt streams of data in a much faster fashion. So within the Mbed TLS security pack, there's the advanced encryption standard, so AES 256 and 512, and a number of other widely used encryption standards are also supported as well. Though I think if you're designing your own system, it would be wise to plumb for the AES standard, as this is the most widely used and the current improved encryption standard. Now, alongside symmetrical ciphers, we have asymmetrical or public key ciphers. So here, if we want to receive a message from somebody, from a sender, we can generate two keys, a public key and a private key. We can then send the public key through an insecure channel, which the sender can use to encrypt data, send us his message, and then we can decrypt it with our private key. So in theory, we don't need to meet the sender to be able to send and receive messages from them. And again, within the Mbed system, we have public key encryption, which allows us to generate public and private keys, encrypt and decrypt messages, but we can also use this system to sign messages and also verify signatures as well. And again, a range of different public key encryption schemes are supported, from the original Diffie DHM method, the more up-to-date elliptic curve digital signature algorithm as well. Now, although in theory we can send our public key through an insecure channel, this is susceptible to an attack called a man-in-the-middle attack, where our public key can be intercepted and then substituted for somebody else's public key, so that this then makes all of our data susceptible to capture and decryption, and allowing then the man in the middle to replay that data with the original encryption key. So if we're using this in a public environment, there's a technique called public key infrastructure, where we have a trusted certification authority who we can give our public key to. They can sign that and create a certificate which can then be downloaded by somebody who wants to send us a message. They can check the signature of that certificate, validate our public key, and then encrypt data, and then we can communicate securely. So this removes the problem of the man in the middle attack. So within the Mbed TLS library, there's support for a standard called X509, which allows us to create and embed certificates. We can sign, write, parse and verify certificates, and we can also revoke them as well. So again, within the Mbed system, this relies on X509 certificates to establish communication between the Mbed client and the device server. So again, if you want to make your own distributed encryption system, it's possible to build that around the X509 certification. And the Mbed TLS suite provides some high-level wrappers that remove the complexity of building up such a system as well. One thing that we'll also need to do within our encryption system is validate the integrity of data as well. And this is typically done through message hashing. So here we can take plain text data of any size. We can pass that through our hashing algorithm, and this will give us a fixed length digital hash or digital signature. So typically this is around about 27 digits, and that number is unique to the input data. So again, if we receive some data, we can calculate its hash, and then we can validate that that is the correct value, that the correct data that hasn't been modified or corrupted. So this is very useful if you're building things like bootloaders and you want to validate the image before you program it into your flash memory. So again, here we can use hashing to validate the integrity of files, but it's also very widely used for password storage as well. So we hash the password, and then that hash can be stored in a public place, so that when a password is entered, we can hash it and then compared to the list of hashes of the original passwords. And again, the security of that depends on having a big enough key space so that people can't simply brute force all of the hash values to work out the passwords. So within the Mbed system, there are a range of commonly used hash functions. So the secure hash algorithms, so SHA-1, 256 and 512. Also RIPE-MD, and there's some legacy hashes as well for MD5, MD4 and MD2. So again, a range of hashes that we're likely to encounter in real-world systems. One step on from a message hash is also a message authentication code. So this works in a similar way to a message hash, in that we'll generate a unique number relates to our data. But that message hash is generated in conjunction with a secret key, so that to regenerate that hash we need access to the secret key. So two people that have that shared secret can generate a MAC, send the data, and then we can check that data with the secret key and regenerate the MAC to guarantee not only the message integrity, but also the origin of that data as well, so we can validate where it came from. So the any of our hashing mechanisms can be turned into a message authentication code. There's a simple algorithm that allows us to create a MAC. So you might think that it would be possible simply to concatenate the data and the message key, so we could put the key on the beginning or the end of the message, create the hash, and that will be a unique data that depends on knowing the key. However, that method is vulnerable to a number of different attacks. So there is a standard method of using a standard hash with an encryption key to create a HMAC, or a hashed MAC. And courtesy of Wikipedia, the pseudocode above is the method that you can use to convert any standard hashing function into a MAC function. Underpinning many of these different algorithms is the use of random numbers. So again, we can have a true random number generator or a pseudo-random number generator, which needs to be seeded with a random number at the beginning. So within the Mbed Cryptographic suite, we have a standard algorithm that's approved by the American NIST, National Institute for Science and Technology, and also the NSA. So it's a standard way of generating pseudo-random number generators. And this is, again, as I say, included within the Mbed suite. Also interestingly, there's a different way of generating unpredictable random numbers, and this is through a method called hardware volatile entropy gathering and expansion. So it's a newer method of creating an amount of entropy within a system. And this really works by harvesting the different states from within the microcontroller that are not generally visible through the application code. So this is looking at things like caches and pipelines, branch prediction units. And this is then used to generate a series of unpredictable random number generators. So we can declare pools of entropy or uncertainty within our system and combine those to create streams of random numbers. So it's a different approach to creating randomness. Also within the library there are a number of support functions which are also quite useful and important. So we have a multi-precision integer library. So many all cryptographic algorithms these days rely on using very large numbers. So these may be hundreds of digits long. So these can't really be worked on with the standard libraries that are within our compiler. So there is a big number library that's provided within the cryptographic suite that allows us to work with very large numbers, and this is optimized for speed of calculation. So you need this sort of library to be able to work with any cryptographic suite. Also there is a syntax called asyn1, or abstract syntax notation, notation number 1, and this is a formal way of describing data that's going to be transmitted by telecoms protocols. So this is a way of describing how our communication protocol is going to work. So if we're implementing our own raw sockets, we can use this to define how we're going to packetize our data. And it's independent of the underlying implementation language, the machine architecture, and the encoding techniques used within the actual low-level protocol. So this is very good in a multi-vendor environment, or where we're transferring data between two different types of system. And again, it's, as I say, an interesting thing to look at. On a more prosaic level, we have also base 64 encoding. So here we can easily convert from a binary string to an ASCII string. So this allows us to transmit data over a channel such as email, which only allows ASCII data. And again, this is used as to encode the data within the Mbed system. So how do we use all of our Mbed cryptographic security library? The Mbed TLS pack is provided as a standard software component within the Kyle MDK. So here within the pack installer we can see the Mbed TLS component, which we can select and install as a standard component within our tool chain. This library was originally created by a company called Polar SSL, and this was a commercial company that was acquired by ARM. So this cryptographic library used to cost several $1,000s. Now it's effectively been open sourced under a GPL v2 or Apache v2 license. So it's free to use, embed into commercial or non-commercial products. So once we've installed the security pack, within the Microvision, we can open the Runtime Environment Manager, and this allows us to add all of the components that we want to build into our platform. So here we can simply add the Mbed TLS library as a tick box and add that to our project, and this will then add an enormous number of files to our project. However, as I said, it's a very modular system. So at the end there is a simple configuration file which includes a large number of hash defines. So we can then simply define which algorithms we want to be included in our project, and then only those will be built and added to our final project. So again, we can very easily minimize the footprint of this library because it's designed for a small microcontroller system. And then if we look through the source code, typically at the end of a file there's a self-test routine with a hash defined to enable it. So again, when you're trying to get the hang of using these components, there's usually a simple example that we can get working to test the algorithm before we start to use it and incorporate it into our code. So again, if you have a look at each of the source code that's provided with the system, you can find these self-test routines, build up and check that everything's working okay. And for the more complex functions or algorithms that are within the code, there are generally, as I say, high-level wrapper functions that allow you to build up a system which requires a number of algorithms to operate. The documentation is perhaps a little tricky to find. It's not available directly as part of the components within MDK-ARM. So you need to go back to the embed.org website, and in there's links to the original developer website, which is now branded as the TLS So there's a number of high-level design documents, sections on how to set up and use the cryptographic library, and then also a full documentation for the API. So once you find that, then it becomes much easier to use. This cryptographic library is currently being built into the ARM MDK PRO. So this MDK PRO provides the networking component for IPv4, IPv6, and currently the Mbed TLS is being used to provide secure application layer services such as secure BSD sockets. Currently secure web server is supported, and then other application layer services will follow in future releases, so things like secure FTP, etc. So this is being used and maintained by ARM. So again, it's an independent cryptographic suite that can be used with multiple vendors' microcontrollers. So I hope that's given you some idea of the Mbed TLS encryption suite. As I say, it has a number of well-supported, well-tested and professionally developed algorithms. It's suitable for use across a wide range of microcontrollers, and you can embed it and use it free of charge. If you have any questions on today's webinar, please either email me or raise a question on the webinar, and I'll come back to you later on. Thank you very much for attending today, and if you want to see any of our earlier webinars, they're available as links on our website. If you can't find those, again, let us know and I'll send you a link to it. Thank you very much.